It is often said that nothing comes from nothing. It's a simple phrase, yet when we project it onto the scale of the cosmos, it suddenly turns into one of the most profound questions humanity has ever asked. How could our entire universe, all of space, time, matter, and energy rise from nothing at all? In our everyday world, nothing can be created without the necessary ingredients. If you want to build a house, you need bricks. If you want to cook a meal, you need ingredients. But what were the ingredients that allowed the universe itself to be born? Today, we invite you to join us on a journey into one of the deepest mysteries of modern science. We will explore what experts think about the idea of something emerging from nothing, how far our current theories can take us, and where they reach their absolute limits. If you are fascinated by groundbreaking discoveries and the grand enigmas of the cosmos, don't forget to subscribe to Orbit Archives and tap the bell to stay updated on our latest content. And of course, leaving a thumbs up helps us create more videos just like this one. Many cosmological theories, whether it's the Big Bang, the Big Crunch, or the Big Freeze, may differ in details, yet they all converge on the same dramatic point, the ultimate end of our universe. According to these models, there will come a time when the very last star burns out. After that, the cosmos will gradually fade into a cold, lightless, almost eerily silent void. In this distant future, supermassive black holes will become the last giants standing. They will slowly consume whatever matter remains, before eventually evaporating themselves through Hawking radiation. As the universe continues to expand, the faint light emitted by evaporating black holes will be stretched across unimaginable distances, until it becomes too diffuse to interact with anything. At that point, all physical processes will halt. For many scientists, this marks the absolute final chapter of the cosmos. But some researchers see this darkness not as a grave, but as a cradle. A few daring theories propose that the end of our universe could be the seed for the birth of a new one. According to these ideas, the cold, empty, stretched out state of the far future might mirror the conditions that existed before the Big Bang. But before we explore how the death of a universe could become the beginning of another, we need to go back to a more fundamental question. How did the first forms of matter come into existence? Atoms, molecules, planets, and stars, none of these existed during the Big Bang. In fact, for thousands of years afterward, temperatures and densities were so extreme that matter could not form in stable structures. What we do know is that once the universe expanded and cooled enough, the first atoms began to appear, built from simpler particles like protons, neutrons, and electrons. Later, inside stars, these atoms fused into heavier elements, giving rise to the chemical diversity we see today. But where did those simpler particles come from? Protons and neutrons are believed to have formed mere fractions of a second after the Big Bang. Before their formation, the universe was a seething ocean of fundamental particles that flashed in and out of existence, unable to combine into anything stable. At this deepest level, physics becomes incredibly abstract and incredibly strange. To understand what came before the formation of matter, we must travel back to the Planck era, the earliest moment of all, so short that even describing its duration feels almost meaningless. During this epoch, the universe was so small and so energetic that the fundamental forces we know today did not exist independently. Instead, three of them, the strong, weak, and electromagnetic forces, were fused into one unified force. The cosmos at this time was a bizarre quantum storm filled with ephemeral particles, including quarks, the building blocks of protons and neutrons. Matter and antimatter existed in almost perfect symmetry. For every particle of matter, there was a matching antiparticle. When they collided, they annihilated each other in brilliant bursts of energy. But even here, we encounter a problem. If matter and antimatter were nearly perfectly balanced, why does any matter remain in the universe at all? Why do galaxies, planets, and humans exist instead of everything having annihilated into pure energy? To explain this, physicists propose that the quantum vacuum, the emptiness of space, isn't truly empty. Instead, it teems with activity. Tiny fluctuations in energy can give rise to pairs of particles and antiparticles that appear and then vanish instantly. These processes happen everywhere, constantly. They are a reminder that in the realm of quantum physics, the border between something and nothing becomes astonishingly thin. But this brings us to an even deeper question. How did spacetime itself arise? Not matter within spacetime, but the stage on which everything happens. This is where our theories shatter. During the Planck era, the concepts of space and time as we understand them simply did not exist. They were part of the same quantum chaos as everything else. To make sense of this era, we would need a complete theory of quantum gravity, one that unites general relativity, the physics of the very large, with quantum mechanics, the physics of the very small. Several theories attempt to bridge this gap. M-theory imagines the universe as a multi-dimensional structure vibrating with energy. Loop quantum gravity, on the other hand, suggests that space itself is made of discrete, tiny units, a kind of quantum foam. In both models, space and time are not fundamental, they emerge from something deeper. The troubling truth is that until such theories are fully developed, we cannot say with confidence what happened at the very beginning. And as of now, physics has not shown a single verified case of something arising from true, absolute nothing. Because of this uncertainty, the ultimate origin of the universe remains open to interpretation. Some explanations invoke a creator. Others point toward the multiverse, the idea that our universe is just one bubble among countless others, each possibly governed by different physical laws. Perhaps the most mind-bending proposal comes from Nobel Prize-winning physicist Roger Penrose, who developed the theory of conformal cyclic cosmology. Penrose noticed that the Big Bang and the distant end of the universe share surprisingly similar mathematical properties. When stretched to their limits, the hot, dense beginning and the cold, empty end become indistinguishable. This led him to a bold conclusion. The end of one universe is the Big Bang of the next. According to this theory, when matter is eventually devoured by black holes and the black holes themselves evaporate into massless photons, the universe reaches a state in which scale no longer matters. In this bizarre, scale-free condition, a new Big Bang can naturally emerge. In Penrose's view, the universe does not simply end, it cycles. Even if his theory is ultimately proven correct, the deeper questions remain untouched. Why does anything exist? What set the first cycle in motion? Can nothing truly exist, or is the very idea physically meaningless? These questions border on philosophy, but even within physics, they remain some of the most challenging and inspiring mysteries we face. Will we ever know the answers? Perhaps. Or perhaps the search itself, the curiosity, the wonder, the endless exploration, is the true gift the universe has given us. Now we turn to you. What are your thoughts about the origin and fate of the universe? Which theories resonate with you the most? Share your ideas in the comments. We're eager to hear your perspective. If you'd like to explore more mysteries of the cosmos, check out the other videos on our channel by clicking one of the images on the end screen. Thank you for watching. Take care, and we'll see you in the next video.